Okay, so mean and variance of probability generating functions. So quick recap here. So should be quite familiar with this bit by now. So the sum of t to the x times probability x equals x. That's the same as the expectation of t to the x, which we looked at a couple of lessons ago. And just to remind you that if you feed 1 into your probability generating function, 1 to the power x is 1. So you just get the sum of all the probabilities, which is equal to 1. So gx of 1 equals 1, just to remind you. Right, I'm going to do some proofs for the expectation and the variance and how to find it. It says in your specification that proofs of standard results may be required. So that's for this and for all the bits we've done so far on probability generating functions. I'm not sure I've seen proof questions come up, but just so you're aware that they might. So that is a possibility. Just stick this blue pen. So we know that g x t, so the probability generating function for x is the probability x equals 0 plus t lots of the probability x equals 1 plus t squared times the probability x equals 2 plus etc. I know not all distributions start at 0, but some of these probabilities could equal 0. So if you're in a geometric distribution, for example, the probability x equals 0 will be 0, and so you will be starting at 1. And then we're going to differentiate with respect to t. So usual notation, you can use dash for differentiating with respect to t. So numbers go to 0, so that's just going to 0. T will differentiate to 1. 2t will t squared will differentiate to 2t. Remember, these probabilities are just numbers, they're just constants, so we're just differentiating the t, and then it'd be plus 3t squared probability x equals 3, and so on. And so when you differentiate, you get the sum of x times t to the x minus 1. So that's times in by the power, taking 1 off the power, times the probability that x equals x. And if I feed 1 through there, so I'm letting t equal 1, then because 1 to any power is going to be 1, that gives you x times the probability that x equals x, and that is equal to the expectation of x. So your first result is that the expectation of x is equal to the probability function differentiated with respect to t with 1 fed through it. Right, similar for the variance, we just differentiate again. I'm going to lose my board a little bit, so I might have to refer back to your notes, but differentiating again. So I'm finding the second derivative. So I'm essentially differentiating, I don't know if you can see that, I'm differentiating this one here. So I think you're okay with that. So that goes to 0. This t goes to 1, so I get 2 lots of the probability x equals 2 plus 3 times 2t times the probability x equals 3. I'm deliberately laying it out like this, plus 4 times 3t squared times the probability x equals 4 plus so I'm just pulling out those constants to start with, and so that gives you the sum of x times x minus 1. So for instance here x is 3, so you get 3 times 2 t to the power of x minus 2 lots of the probability that x equals x. I'll let you think about that. So when x is 4, you get 4 times 3 t squared probability x equals 4, and that pattern is just going to continue. So we can sum the whole series, and again we can look at feeding through 1. So I'm letting t equal 1, and so similarly 1 to any power is 1, so the t's aren't affecting the rest of it when you let t equal 1, which takes me to there. And then if I multiply out this bracket, I get the sum of x squared times the probability of x equals x minus the sum of x times the probability that x equals x. This is the expectation of x squared, and this is the expectation of x. And so if you remember, the variance of x is equal to the expectation of x squared minus the expectation of x all squared. So you should know that from maths. No, is it maths we did that? Or it might have been in discrete random variables. We did that in further maths actually. So you should know that from first year further maths. Sorry, I've just realised I'm coming off here. Just save that in time. There we go. So expectation of x squared minus the expectation of x. And so the variance of x is equal to this lot here. So it's the second derivative of the probability generating function with 1 fed through it. And then I want to add on the expectation of x. So that gets rid of that. And then I want to take away the expectation of x squared. And so sort of writing that down in terms of derivatives. So it's the second derivative with 1 fed through plus the first derivative with 1 fed through minus the first derivative with 1 fed through squared. That takes you to there. So I hope that's all okay. I'll go over a couple of examples of actually how to use these in context of a question in a minute.